Hello. Oh, it works. Nice to meet you. My name is Sasha. Today we will have a little presentation about Waku. It will be two presenters, me and Ivan. We will explain you overall problematics of peer-to-peer networks. We will go through common parts of peer-to-peer networks, challenges that are faced usually, and how they usually are dealt with, and the common trade-offs. Then we will explain a bit about Waku, which is a functionable peer-to-peer network that has some answers to some of the problems that will be mentioned. And we will show you some examples, and we will try to do a bit of programming. So yeah, how are you guys familiar? Raise your hand if you are really familiar with peer-to-peer networks. You build one by yourself. You know ins and outs of P2P or Dev P2P, or you build your stack. So maybe you can enjoy this talk, I hope, as well. But otherwise, it's more of an intermediate level. So yeah, let's start. So why do we even care about peer-to-peer networks? So first of all is that due to architectural decision of going with peer-to-peer, we guarantee some potential decentralization and censorship resistance that comes out of it. And why do we even want it? Is that because we are in crypto space, right? I think this is like something that does not need a lot of answers. But then usually this solution is made to introduce some degree of privacy and data ownership. It's to provide this service to the users of our applications, networks, whatever. Other properties that peer-to-peer networks guarantee is that usually they are fault tolerant or resilient. And this comes out of the fact that we don't have single point usually there, and we can survive as a set of nodes if one, two, or even half of the nodes are offline or down. And then potentially we can get some scalability out of this decision. This is questionable actually, because peer-to-peer networks are known to be difficult to make right. But hypothetically, we can reach a high degree of scalability naturally. What challenges there are? So first one is that we need to build one and maintain ourselves. This is challenging because the peer-to-peer networks has a lot of complexity in it, like some set of protocols being implemented, so we need to make sure that all the peers understand each other, and then if we, let's say, release a new version of our software, we need to make sure that it somehow like gets propagated or something. This is quite challenging, as well as there is a lot of DevOps involved. Like whenever we upgrade something, something might be down, then it impacts some other people. So it's difficult to do right. Reliability is also a big challenge in peer-to-peer networks. Why? Because it also depends on the degree of nodes, amount of nodes in the network. The less there are, the more reliable it is. So like if there is one node, it's quite reliable. If there are more, then it becomes challenging to make sure that all the protocols function correctly and the nodes propagate the messages in the right way. Then network discovery is a huge bottleneck there. All projects made different decisions there, but more or less there are some patterns that everyone follows. And security and traffic management. Like depending on the architecture of the peer-to-peer network we go with, we incur different pattern of how data will be propagated. So let's say for the case for Waku that later will be explained by my colleague Ivan, Waku goes with a gossip sub architecture, and it incurs some particular way of how message is going to be exchanged in the network. Other people might go with a mixed net or something else, so depends. And for the security, there are more parts than just encryption, that other people cannot read your data. There is also a security of overall network. How like identity theft, like let's say if someone can pretend to be someone else in the peer-to-peer network, it's quite challenging and has to be addressed on a software level somehow. so we can use different algorithms here. The other problem there is that how to make the network not to go down because of like someone malicious there. Let's say if we have a peer that produces 90% of the traffic overall, right? We don't want a single node to consume all the resources of the network. Yeah, so this is a security question as well. How to build a peer-to-peer network? So these days there are a couple solutions. Usually everyone goes with CERT, do it yourself, DIY. Many projects just go there, try to figure it out. They figure it out somehow because all of us are quite good engineers, I hope. And all of them just answered the questions, solved it, and release. They use just not the network stack, whatever is available in the language of their choice, and that's it. But other projects has figured out that it can be scaled somehow. So Dev P2P and Li P2P got born. So they appeared approximately at the same time. Dev P2P is very dedicated for Ethereum stack, and it's like something that all Ethereum nodes implement. But there is also Li P2P, which was more of a generic stack. Like it can be used by any project. It does not have any dependency on any blockchain whatsoever, and it's very modular. For Waku, it is the case that we built on top of Li P2P, and we extended with our protocols. We continue building from there. So shared parts. It also somehow related to the challenges that I mentioned. And usually we care about peer discovery in the peer-to-peer networks, right? This is obvious. Unless we know our peers, we cannot form a network. And there are multiple choices that projects go with. Some of them are DNS discovery. We call some particular, we retrieve some DNS records. From there, we understand like this is a set of nodes that we can use, and we go on with them. Some choices might be like an exchange, further exchange. Like we ask the nodes if they know other nodes, right? So very natural way of discovering a network, same as humans behave. Then informational exchange. So a format, usually the networks try to converge into one format, so hence there is some specification for a package of data that is going to be populated throughout the network. Then something specific to the networking in the internet is that some peers might be hard to reach, so hence we need to use some hole punching techniques, which means that if I cannot dial you directly, maybe we can bypass it somehow, like you dial me instead. Or let's say if it is not possible, it's approximately I think 30% of the users overall, which is the case for some protocols. We may do relaying, which means that I am going to ask some other peer to relay you some data that I want you to see, and you do the same. So we like bypass this wall in between us. Then the other shared parts is that all the networks try to somehow secure themselves from DDoS. So hence some DDoS protections comes in play, and spam protection. How it can be addressed by different meanings. Usually it might be like some token exchange. There might be some common shared record of peers that are like reliable, whatever they can be used, can be trusted. So different ways. But one of the most difficult parts here is that it's hard to make it in a privacy-preserving way, so that we don't release some identity, or we don't even know who his peer actually is. And Waku has found some answer in partnership with other projects in the space. Other shared parts is that transports. So this one is very important because if our nodes in the network implement more transports, such as WebSocket secures, TCP, UDP, WebRTC, Web Transport. The more transport they implement, the more clients they can reach. Like let's say if we have a WebSocket implemented, we can be sure that our node can function not only between like some servers, right, but also with browsers. So hence we can serve more users. and much more. So there is a bandwidth management, like how to make sure that our nodes are very ecological in the resources that they have, the reputation, like we want to make sure that the peers which we are talking ad hoc right now are more or less fine or not. Encryption, this is a huge question as well, like we don't want the whole network know what we are talking about, what we exchange, right, and routing, more or less. So hence there are some trade-offs that we make while building the networks. And one of them is that do we want to have one huge network, or we want to have like some sub-networks that somehow talk to each other later on? I don't know. If we do some sharding, how many of them we want, like 1, 2 groups, 3 groups, depending on the content exchanged maybe, right? So this is a conscious choice that we as developers have to make here. Then a message size, right? A data packet. The bigger it is, the slower propagation of it will be through the network, regardless of the architectural choice of it, right? So we want to be cautious of it, and we want to make the best choice for our particular need. And then rate limiting, right? We don't want anyone spam the network, consume all the resources. So which technology we use? Are we fine with having, let's say, a common ledger of trusted nodes, or we want to be more open, like publicly available networks that anyone can join? So in that case, what do we do? How do we address it? I don't know. It depends. Incentivization, right? So some of the projects, public networks, have no incentivization, but they still function well. And why it happens is that because people share a common cause. They want to be part of this network because it, let's say, gives some privacy. It gives underprivileged people access to internet without them fearing for any consequences or something, or just buying drugs, whoever, whatever. And discovery protocols, like there could be a different way of how we can discover. So we do some trade-offs here as well. Some can be slower, some can be faster. And what Waku does. So here I'm gonna pass it down to Ivan, and he will tell you.
Thank you. Thanks. Hello, everyone. Okay, and in this part of the talk, we are going to overview the actual implementation of the Waku protocols. As my colleague mentioned, is an opinionated implementation of our view of how we consider is good to solve the well-known problems such as the discovery, the problem of a NAT or a firewall, the problem of routing. This is covered by all of the protocols that are shown in this list. And aside from that, we introduced a new one, which is the RLN rate limiting one, and we are going to cover in a few seconds. Okay. Regarding discovery, we have 3 main discovery protocols. One is peer exchange. This is pretty centralized and is not ideal, but is useful in certain conditions. And what it does, sorry, what I'm explaining is not shown in the screen. But what peer exchange protocol does is it asks to other peer to share the peers that it knows. And it's just a request-response protocol where the other peer responds about the information of its peers. And then we have the DNS discovery, which is a very interesting protocol that is powered by DNS. And then we have the Discovery v5, which we consider to be more decentralized and more convenient for the Web3 scenario, and its implementation is based on Kademlia, and well, as you know, is the DHT, and what it does, it retrieves a random set of ENRs, and yeah, this is very intensively used in Waku. Okay, then regarding Another family of protocols that we have in Waku is the request response protocols, which are, you will see in this talk that we have two main families of nodes. We have what we call a full node, which is basically a node that is part of the overlay of the network and produces the routing of the data. And then we have the edge nodes. And for these edge nodes, such as a mobile phone or a browser, it cannot participate in the routing protocol because it's data consuming. And for that reason, we created these request response protocols for helping, in order to help these edge nodes in different ways. For example, regarding the store node, its main purpose is to allow nodes to come, when a node come back to participate in the network, to get back the latest state of the messages. Then we have the sync, and the main purpose of this protocol is to make sure that all the store nodes have the latest state and the same state of messages. Then we have light push. The purpose of this protocol is for edge clients to be able to participate in the network, to publish messages, and filter in the other way around. Okay, if we go further to the routing protocol. Oh, sorry. Anyway, okay. Okay, regarding the routing protocol, is we call it relay, and it's a kind of opinionated version of Gossip's app, which is great and is very interesting. And we're going to cover very briefly how Gossip's app works in this talk. Okay, this is a very simplified schema of pretty interconnected network, and the dots just represent nodes. And as you can see, all of the nodes, they are continuously exchanging control messages. Like, for example, the messages that I saw, the messages I'm interested in, and the control messages names are I want or I need. No, and then we have the Waku messages. That these are the actual messages that transport data in the network. Something important to bear in mind is that we can have, for example, 100 connections to 100 nodes, but one single node will spread data, Waku messages, to up to 6-8 nodes maximum, and every node will pick up the best from its neighbors, will pick up the best nodes regarding according to certain parameters, such as latency, number of messages per second, how responsive a node is, and so on. And okay, and how does it work? Every node has a heartbeat that happens every second, and on every second, every node measures or gives a certain score to all of its neighbors, and according to this score, if the score is too low, then it ignores the node. It doesn't mean it completely disconnects to the node. It keeps gossiping, asking what messages do you have, what I have, etc. But it doesn't participate or interact sharing important data, no? And it only establishes a mesh with amplification factor of a value between 4 or 8. This is how we are configuring at the moment. And yeah. And in this slide, it's just a simple example of how a single node establishes at certain point in time what is the about its neighbors, what is the peer score, and for example, if node A receives a message, then given that the overlay network is established with B and D, it will only spread the message to B and D, and not others. And something important to bear in mind is that this can change every second. It's not a fixed overlay network, but it's something that is alive. Okay, and then we have the red limit nullifier. This is a very interesting topic and very interesting technology because it allows to protect the network against spam in a private way, so that the node can prove that it belongs to the network without actually disclosing its information, or it's very cool how it's implemented, and it's based on CK-SNARK technology, and keep a smart contract currently in Sepolia, where the membership set is configured. I think we are about to release version 2 of RLN, and yeah, it's basically this is a quite complex topic, and it's beyond my knowledge. But just to get an idea, the main purpose of it is to protect the network against spam in a private way. Okay, regarding the Waku message, as you remember, this is the one that is being sent across the overlay network. Basically, it contains a bit more fields than shown in the left, but basically we have a payload for which we don't impose any additional encryption. We leave the encryption to the app developers. And regarding encryption, it's important something to notice that there is point-to-point encryption inherited by the libp2p, which is made following the noise protocol. And we have the content topic, which is a field useful from for example, in the filter protocol. An edge node subscribes to a certain content topic, and from all the information that is shared across the network, the messages the edge node is interested in is going to be sent to them. Okay. And regarding this point.
Okay, so to build on top of Waku, I just gonna introduce you a bit to CDKs that we have and languages we support. So this QR code leads you to documentation website. There is a lot of information, links to our communities and such. If you have any questions about anything like Waku related, code is failing, behaves unexpectedly, reach out to us. Everything is there. But we do support JavaScript and TypeScript right now, and NIM is and second language that it's more of a first language, but still it's the language of our choice, and we have an implementation of Waku in NIM language, and it's compilable to C, and you have the C artifact that you can consume later on. We're also working on better Go bindings and CDK and Rust and Python. They are work in progress, but can be used to some cases right now. So for GS Waku, we have like a couple of packages. Main one is Waku SDK. Just install it, use it, it's gonna work. I hope so. Then we have a wrapping for React. Also deals with React lifecycle methods and stuff that busts a lot of creates a lot of unexpected behavior. Then we have a create app that can bootstrap your application quite easily. Might be useful as well. So the main users right now are Status. Status is a messaging application which is dedicated for one-to-one chat as well as communities, and it uses Waku underneath. It has its own set of nodes that are operating. There are a bit different guarantees than defaults that we propose projects to use, such as a bit extended store retention, right? Because such applications want to retain data longer. Then a second project that uses Waku is Railgun. This is privacy-oriented DeFi project, and Waku is used for broadcasting fees in the network so that it's not known where it originates from. Then the Graph also uses Waku for information exchange between some of their nodes. Yeah, so and use cases, there can be anything, such as DeFi, as I already mentioned, community-run apps as well, some social interactions, wallet-to-wallet communication, gaming, you name it. So we saw interesting applications even with geolocation positions, such as users' geolocation gets mapped to a particular namespace in Waku network, and then you can talk to the room in which you are located. Quite interesting approach to create a layer on top of reality. So today we're going to show you some of the examples. This link will lead you to a repository with our examples where we experiment, where we play around, and as well as do something for users. I will show you an application named Bodybook. We created it as a POC just to show people around here at Devcon. And there will be more examples, and we can try to do some programming if you are interested. Otherwise, I will just walk you through some simple one-page JavaScript application with request response protocols that are used. Do you have any questions at this point? Maybe we can do a quick Q&A before we go into some code presentation. Oh, yeah, there is a question. Sorry.
Specific for native mobile SDK?
So do we have a mobile
like
SDK?
Java or Kotlin or Swift on your plans, I mean?
Not now. We have it in plans, yes. JavaScript version can be used in React Native. We did some bindings. We didn't prove it working reliably, so this is also work in progress. We had some Waku being adapted for running is also in React Native or other stuff, but also Status is using Waku as well, but they did a little bit more work than just installing it. So it is work in progress. Yes. So please.
Is there a public network that the Waku nodes run on, or are you expected to run your own nodes for the applications that you run?
Yeah, so the main difference between Waku and, let's say, P2P, as I mentioned, P2P is a stack that we are using, and anyone can, let's say, me, you, we together want to build a network, we create an application out of P2P, right? What Waku does differently is that it provides a set of protocols, like solutions to some problems that we observe and we want users to have dealt with, as well as we have a running network, which is called the Waku network, TWN, and I will show you how to join it, let's say, from JavaScript CDK in a couple of lines of code, and you can hook in your own nodes to it, or use it as a signaling node, let's say, to create your own subnetwork or something like that. Yes. Any more? Okay, so I'm gonna go to my laptop and let's see what we can do with the code today. So this one is for example with Rust. it uses a NIM version of Waku, some bindings, and you can scan it and see how it is implemented. Later on, Ivan will go and present himself the code and walk you through it. So bodybook, if you scan, this will lead you to the source code of the simple one-page application. Otherwise, you can visit bodybook.fun. And what it does is that once you open it, you can create a book. And then later on at the conference or somewhere, you can come to people and ask them to sign your book, like collect signatures. These signatures will be created from a wallet, right? So let's say a MetaMask wallet or something. And the interesting point about this application is that the signatures will be exchanged through Waku, and they won't be committed to the blockchain. Hence, there will be like an easy propagation of this information, and it will be stored in the store protocols that Ivan mentioned about. So here we have like a couple of you know, just books, whatever, and there are some signatures attached. Yeah, so if you create it, it's gonna appear here, and yeah, so this is very simplistic application, but still very interesting use case. Yeah, okay, so then you can run a node. This is another application example of how Waku can be used. You can be just a node operator, so contributing to the network. Let's say if you have a spare Raspberry Pi 4 gigs of RAM or something, just opening a Docker and doing one line can already contribute to the network quite a bit. Though I'm lying, it's not one line, it's more of one line to run in your terminal. And now if you open this link, it will show you a basic JavaScript application. It will lead you to the code, which I will go and show now. I hope you see it well. Yeah? Is it readable? Should I increase it a bit? Okay, a bit. This is just single one file application which consumes JavaScript CDK. And you have to create an instance of a node first, right? So hence this create light node function is used. It accepts like different parameters. There you can pass particular coordinates of the network that you want to use if not a default network is in use. So by default network, I mean here TWN. And if we want to use a default set of configuration, we just pass default bootstrap. Other thing that Waku has in it is the message, the data packet, right? It gets propagated through the network, and there are some properties of this data packet that help to do routing. And one of them is content topic, and content topic should be perceived as the namespace under which data should be exchanged from the perspective of an application. So let's say if I'm in an application like Telegram, right? A content topic can be one chat, one group in which the messages are getting exchanged. So hence, I am, as a user, have a set of chats, and only from them I want to receive messages. If they are coming from different chats, I don't want to receive them. That's the simple idea here. So, and as anything in the computer science, we want to create a reader and writer. We have a blob of bytes being exchanged in the network, and these two lines are doing exactly this. They create decoder and encoder, and they are configured to be using one particular content topic. Later on, we have to start the node just to initiate the process as part of API. And the second line does an important part, is that we block execution of application until we receive some peers. This is just one way to do it. Another way might be to not to do it and rely on lazy connections that will be managed by GS Waku in that case. So then here I'm going to show two protocols through two lightweight protocols that we have for edge nodes, as Ivan mentioned. One of them is filter and another one is light push. They come complementary. And for filter, the main use case is that you want to receive only those messages that you are interested in without consuming a lot of bandwidth, etc. And filter exactly does the same. We send a request to a service node and we ask it to later return a messages to us. The whole interaction happens over WebSockets as of now. In future, we might go into having a web transport, which is work in progress right now, as well as WebRTC might be in use for some cases. But regardless of it, we rely on the service node to return us messages. In that case, we can do a lot of heuristics. As I mentioned, peer-to-peer networks are not ideal. Some of these problematic parts are having unreliable nodes. One node can pretend to be reliable by advertising itself with some protocols that we are interested in, but it might not do what we want. What we do in that case, we implement some heuristics inside, such as if I sent a message and I didn't receive it back from that node, it's probably not reliable, I'm going to drop it. So this is a part of overall umbrella term reliability, which we were working for the past 6 months. So yeah, this is a simple callback from JavaScript perspective, nothing fancy. As to pass data inside, we just, wait push. So here, just one for loop, sending 10 messages from our side. And the send is exactly send. It's just one request over existing transport. In our case, again, it's WebSockets. It just creates a blob of bytes and sends it. Yeah, so let's see into action. Okay, so I'm going to open localhost. I have it open, and yeah, there are two tabs. Here we want to reconnect. Here we want to reconnect as well. To do, we are waiting for peers. No peers available. Something happened. Good. Here we subscribed and here we subscribed. So now we are sending some messages in the loop and we are receiving some messages. As we see, one of the properties of the network is that how Waku functions is that we're going to receive our own messages. And this can be quite useful for some of the applications. Yeah, so this does its thing, so it works. One of the interesting things is that there are a lot of logs, error logs. They are expected as for they cannot be ignored. Are there any questions right now? Yeah, please. Can you repeat to, yes?
Yeah, the light node instance, it's not a P2P instance.
No, actually it is. So, but it depends, right? There's some trade-offs that we have to make in the browser. One of them is that a set of available transports for the browser tab, right? Browser is a very restricted environment. There are a lot of things that we cannot do, such as we cannot do a TCP connection directly or UDP connection directly. We have to do either HTTP or a WebSocket connection. That's it. WebRTC as well, but there are limits, right? So, and also resources. Browser is very limited in how much computation we can do, like heavy computation, right? The browser tab can become suspended quite easily by operational system. Everything stops working in there, right? And it cannot be a fully functional part of the network. Hence, we call it an edge node, meaning that the traffic kind of ends there, right? It does not participate as a full node, it's not full. But it is peer-to-peer in the meaning that the browser tab is independent in how it discovers the network. It uses almost everything but discovery Wi-Fi that Ivan mentioned. It discovers the network through DNS and peer exchange. And as for our case, right now we have 24 peers. So right now we have 24 WebSocket connections to 24 full nodes that we can use interchangeably or in rotation or If we observe that some does not work, we can use others. And if others does not work, we can do something else. And also the peer exchange is an ambient peer discovery, meaning that it happens always in the background. So, and we can see that we have quite a few nodes collected right now. Right now, 25. But the longer the browser tab will be executing, will be open, the more peers we're gonna discover and use eventually. So from that regard, it is peer-to-peer, and it owns its own stack as to like encryption. Yeah.
So this provides like a WebSocket server. So all these nodes provide a separate WebSocket server for these edge nodes?
Yeah, exactly. This is very interesting because we can reason about it as to having a serverless application. We don't have kind of server, but we still can have a connection in between them, right? It's backendless. Yes.
And I mean, one thing from the previous slide I have was the syncing, right? So how does the syncing works? Because you said you only send messages to like 4 or 5 peers at a time. So how does it know like the message?
Yeah, so how does the node knows where to send the messages? Yes, was that the question? Yes, so Gossip Sub is not a directed way of routing the traffic, and we rely here on eventual consistency, let's name it like that. We know that the node will relay messages to its peers. In our case, it's 4, 5, 8, something like that, right? And we know that all the peers kind of connected to each other, right? We have it as a graph. So if someone originates with a message on one end, by the rules of Gossip Sub, it's going to propagate till the other end. But it can take a lot of time as well as little to time, right? We don't know where the node is placed in the network. And I don't mean geographical position, but like logical from the Waku standpoint. Yeah, so in our simulations, we had simulations like up to 10,000 nodes. And we had the numbers as to, in average, from 200 to 500 milliseconds was the message propagation. In current TWN, which supports RLN as for the meaning to shield from the DOS, we have like 1,000 nodes, and the message propagates quite fast. Yeah.
And so if the node is offline and comes in, right, does it get the older messages that were broadcast?
Yeah, this is why we actually came up with store protocol, right? In peer-to-peer networks, we kind of think about the transport, right? These are nodes, they talk to each other. A store, everything else is like application logic. We agree with that, right? At each application that uses, let's say, Waku stack or the network needs to implement its own stuff on top, a store including. But we still understand there is a need to have a short-lived, like while I'm offline, let's say for 1 hour, right? I still want to get back these messages. So store is for full nodes, and it's going, once, let's say your full node goes offline and goes online back, it's just going to ask the peers around for the missing messages through the store protocol, and it's going to do the sync. Thank you. Any more questions? No? Let's see something with Rust been done, and if you want, we can do some programming or something.
Okay, thanks, Sasha. Okay, in this part of the session, we're going. Is it visible? We're going to cover a few examples regarding the Waku Rust bindings. By the way, credits to Richard for the great job in this repo. And this is the in there. Well, in QR shared earlier on by Sasha, you will get a branch to this where this is implemented. And let's first of all overview the repo and what we have in there. Basically, we have Waku SEAs, bindings, and the examples. And in Waku SEAs, this is the one that implements the NWaku. This is the NIM implementation. And from here, we've created, or we are working on the creation of C library that exposes all the functionality that is available from a Waku node, the discovery, the creation of a node, connection to another peer, hole punching, etc. All the libp2p protocols that we've mentioned earlier on are covered by the NIM implementation. And in this C library, what we are doing is we are exposing these features through FFI to any other languages. At the moment, as Sasha mentioned, we are covering Golang, Rust, Python, C++, and Node.js. Okay, let's carry on in this particular case. Then we have the Waku bindings crate, and what it does is a lib crate, which is just a wrapper around the Waku SEAs. And in there we have the implementation of the bindings stuff. And all the complexity is tackled within this module. And yeah, you will see that we apply a technique called trampoline, and that helps us to interact with Rust. With the libwaku library from Rust. And then we have in this particular case, we have a few consumers, and this is just a simple application. Well, it uses Tokyo as a sync framework, and what it does, it basically at first it creates a Waku node with certain parameters. Then it establishes the DNS discovery URL. This is for retrieving the bootstrap nodes. In order for the node to start participating in the network, it needs an initial help. And for that reason, we have this. And from there, many other nodes can be inferred. And then we start this discovery v5 protocol, which is in charge of discovering other nodes in a decentralized way. Okay, this is part of the example of this application. Maybe the example is not super idiomatic in terms of Rust at the moment, but it's just a proof of concept to see how a Waku node can be integrated in Rust. And in this particular case, the main purpose of the application, or what the Waku node is used in this case, is just for sharing the game state across users, across the players. Okay, and given that we have a user interface and something important to bear in mind is that the incoming messages by the node, these messages are being handled by the libwaku, which is implemented in NIM. And something important to mention is that this Waku node is running in a separate thread, and we need to, and the libwaku establishes a communication with this thread. This is needed because the NIM runtime should run separately from any other runtime, such as the Rust, Golang, Node.js, etc., in order to make it work properly. Because as we are using nowadays NIM, we are using it with a garbage collector, and it needs to run on its own thread. And something I wanted to mention is that all the incoming messages, they come in this closure. In here, as the example is implemented now, it starts the Waku node, and then we pass. We subscribe the node to a certain topic, just the game topic, and we pass a closure, which is in charge of getting the incoming messages. And with this, what we are doing is we are notifying the main thread about the incoming message, so that the game state can be updated when new. And now let's do a small demo. In this case, just we have two instances of the tic-tac-toe application. On the left, each of them is running a Waku node. Then we say this is going to play as X, and this is going to play as O. Then they can play, and well, it's a very simple example. In this case, player X won. And okay, something else I wanted to share is in this presentation. Sorry. Feel free to clone this example because we are going to play a little bit with it. It's just you will find it in the same Waku Rust bindings repo, and it's a bit more simpler. And what it does, it creates is more or less the same, but more simplified. It creates a Waku node. We are passing shards. This is the shard thing is something that is needed to split traffic in a certain way. It can be understood as a way of channels or communication channels in Gossip's app. Then we are establishing maximum of 1 megabyte log level. Content topics. Sorry, no. This is the pub subtopic. We set the keep alive to true, and as we saw earlier on, we enable the DNS discovery and disk v5. Okay, and in this case, after that, after creating the node, we just start it. And then we establish, we subscribe to the Waku, to the topic, and that's it. And in this example, it just creates a node, starts it, subscribes to the topic, and just wait until a Control C is pressed. And if we run it, we will see that Yeah, these logs are coming from the implementation of NIM Waku. Yeah. Okay, and as you can see, the node is starting to receive relay messages because it's subscribed to. And yeah, and that's it. And we are receiving messages from the network. I believe they come from status because I connected to the status network. And well, just that's it. I don't know if there are questions or comments, or would you like to see something else, or?
How is the DHT look for the network? Like, what flavor of DHT?
How's the DHT lookup being done, or you mean? Yeah, we have a Discovery 5 client, and it performs a request to the network, and it's.
But so, like, how does it decide where to route the message? Just on the peer scoring, or what?
You mean yeah, exactly. The messages are being routed by a healthy mesh. If there are peers that are misbehaving or are spamming the network, then they are blocked and they don't participate in the network. Okay. In that case, if no more question, thank you so. Yes. Yeah, thank you for the question. Good question indeed. As Sasha mentioned, the gossip sub itself, it doesn't guarantee a certain message to reach a certain point. And for that reason, we are working on implementing what we call reliability protocols. And somehow we add an additional layer of redundancy. And there is sorry, I forgot the precise name, but one previous implementation of, or one enhancement is to consider that one message has been received properly if it has been received by a store node. So we somehow we use the store node as a leverage to reinforce the transmission of a message. But yeah, indeed, this is a very big problem that we need to overcome, and yeah, we are working on it. And thank you. Any other question? Okay, in that case, thank you so much for the time, and see you around.